Now let's take a look at the second law of thermodynamics. Let's imagine that you have a gas at some temperature TH, and we want to extract some heat from that gas to do some work. So we can do that. We can extract heat from that gas and do some work, but there's always going to be some waste heat. And that's going to be dumped into what we call our cold reservoir. So there's no way to do this where QC is equal to 0. In other words, there's no way to do a 100% extraction of heat to work. If we're extracting heat, we can do some useful work, but there's always going to be some waste heat. And we can write that down as the efficiency of this type of heat engine. And the efficiency can be written as W, the work out, divided by the amount of heat in. So you can think of this as like what you get from what you put into it. And I know from conservation of energy that the work has to just be the difference between QH and QC. So I can write down QH minus QC divided by QH, and that's just going to be 1 minus QC minus divided by QH. And since QH is always going to be larger than QC, this efficiency always has to be less than 1. Now there is kind of an ideal process that'll get us as close to this as possible, and that is something called the Carnot cycle. And the Carnot cycle basically minimizes the heat loss in this cycle from one part to another. So if I have the PV diagram, the best way to get my heat engine to minimize loss of heat is to have a couple processes that are where the heat is equal to 0. So I need to have some kind of adiabatic process in this. So let's go, we're going to go from point A here, we're going to go isothermally to point B. Then we're going to go adiabatically to point C. We're going to go isothermally back to point D, and then adiabatically back to point A. Draw that right. So this is an isotherm, constant temperature, this is an isotherm. Constant temperature, this is an adiabatic process. And this is an adiabatic process. So in these two legs right here, the heat lost and gain is 0. And so that means that we're going to be able to maximize the amount of work, which is the area under this curve, and minimize the amount of heat. And the efficiency for a Carnot cycle we can change to just be 1 minus the ratio of Tc to Th, where Tc and Th are the temperatures of the hot and cold reservoir. So again, you can see that we cannot get 100% efficiency, and in fact we can't even really get all that close. If you imagine realistic values of Tc and Th, if you imagine, for example, your gasoline engine, Tc is going to be air temperature, which is like 300 degrees Kelvin, and Th, because of the processes involved with the combustion, are going to be something like, not much more than 1,000 degrees. That's probably as good as you can get. And so the theoretical efficiency would be 1 minus 300 divided by 1,000, which is 1 minus 3/10, and that's only about 70%, which, is high, but not great. And your engines don't operate at anywhere near 1,000 degrees Kelvin. So efficiency is something that, you're not, even in a Carnot cycle, which is ideal, is not going to be anywhere close to 100%.